final answer you are telling. Delta S.
Yes, sir.
Any difficulty? Is this okay? This one you already calculated, right?
Yes, sir. That only came out to be 0.04.
And this one you converted?
20. It is taken as such, right? Joule Kelvin is there.
Yeah.
Yeah.
Because you are already
Yes.
multiplying it here.
Yes, sir. This only I did. I'll check it, sir.
Mm-hmm.
Yes, sir. 0.709.
So when you have an increase in temperature, the change in entropy is entropy change. You should increase or decrease.
Positive.
If you have
Decrease.
increase in temperature.
Positive.
See, entropy is, in other words, a measure of disorderness of the system. If you increase the temperature, the disorderness in the system should increase or decrease.
Increases.
Increase, sir.
So you should expect a positive value or negative value, delta S.
Positive
Positive value.
value.
Yes. Is there any difficulty for you to arrive at this point?
No, sir.
Is this straightforward? Any doubt? If you have any doubt, you can ask me. I can explain it. No problem. Okay, if that is fine, then moving forward, this is how. So now, in terms of when you are measuring the entropy, you have two chances. In isothermal conditions, you have you have to consider the T is constant, so volume change only will appear for you when you are measuring the change in entropy. Whereas when your volume is constant, okay, sorry, when you are doing adiabatic process, you have a change in temperature, so you have to your formula will be delta S is equal to C ln T2 by T1. This is how you can measure. Now, when you have both the things together, when you have a change in volume as well and change in pressure as well, then how to calculate this one? So this example will give you an understanding of the measurement of entropy, total entropy change when you have a change in temperature as well as volume.
We have to sum up both the expressions, sir.
Yes, yes, because it is a state function, you can sum up. See, you are directly given n value that it's a compression, the change in volume. In the process, you have a change in temperature. What is the change in entropy of the gas? So now, straight away, you can calculate the change in entropy due to change in volume. Since it is compression, the disorderness of the system should
be negative.
decrease. So you will have a change in entropy.
Minus.
Okay.
So yes, it's a minus 13.3832. Right, so equal to
Similarly,
13.
if you go for the other case, when you have a change in temperature, now you calculate for change in temperature. CV value is not given to you here. Maybe they might have taken it from the standard values for argon. That should not be an issue because it will be given to you in the exam. So your delta S is?
Sir, this is coming out to be
Sorry?
0.242.
Any issue?
This delta S is 0.242.
0.242. Okay, fine. Maybe on decimals. Maybe we might have taken some decimals different. So it is very close, right? You are telling that it is 0.242.
Yes, sir, 0.242.
Oh, that's fine, no problem. You are so close. So overall entropy is
We
the
have
sum of the
to,
change due to volume and temperature. So overall what you are getting is the total entropy is decreasing. That means entropy change due to volume is more than entropy change due to temperature. What is the temperature change? 22 degrees of volume change, 5 degrees centigrade. So that's how you need to calculate when you have.
Yep.
So that's how you need to calculate when you have.
So can you please go back to the previous slide?
Yes, please. Yeah. You are copying?
No, sir.
Any doubt?
No, sir. I'm trying to understand the question.
Okay, okay. The question says that the argon gas is compressed, okay, in a quick way. It's very fast compression. So when you are doing very fast compression, you cannot do it in isothermal conditions because you know the reversible case. We have discussed the reversible expansion and reversible compression. There what we do is that infinitesimal change of temperature at each stage we follow. That means that slowly we are changing the temperature, whether it is a decrease or means we are maintaining the thermal equilibrium. When you have anything abrupt change, you will experience a change in temperature. Since it is a sudden compression, they experienced a change in temperature. That's what it is. So otherwise also the question is straightforward. You have given that volume is changed and then temperature is also changed. Any doubt in the question?
No, sir.
no, sir.
I don't know who was asking.
Sir, what is the thread point in the graph?
Which point? This one.
Sir, in this graph, yes, sir.
This is temperature. Starting
No, sir.
temperature.
I understand that straight line equation, but what is this one? The horizontal line?
This line,
Yes, sir.
that red color line.
Yes, sir.
Oh, they are indicating that this one delta S
Sir, it's decrease in volume. From
decreasing.
volume, we are getting that, right? From 5 to 1. The entropy should be negative.
Okay. No, I
That
don't.
that line that line indicate that point, right?
They
Sir, there is
So
a
that's a
arrow mark saying reversible. That one only I don't understand.
okay. Maybe that if you do the reaction in reversible conditions, okay, the entropy change will be this much. Since you are the conditions that you are doing this experiment is irreversible conditions. Whenever you have told that this sentence, write this word suddenly or abrupt or something, it's an irreversible condition. This is indicating the change. When you have a reversible change, if you carry out the same volume change in reversible manner and irreversible manner, the change in entropy that is indicated. Is it convincing?
But in this case, the temperature is remaining constant in the horizontal line.
Yes. The when you are doing this changes, the what is that? The, when you are doing the reversible changes, okay. So you never do the compression abruptly, okay. So you are always keeping that equilibrium. Slowly you are decreasing the volume. You are doing compression, right? At each
Yes,
stage,
sir.
each stage, your system is in equilibrium with the surroundings. That means
So
that
the temperature remains constant, sir.
P external pressure and internal pressure does not vary much. At any case, you can revert back. Suppose you are compressing, right? You are compressing. That means that P external pressure is higher than the internal pressure. So at any point, by an infinitesimal change in the pressure, you can also do expansion. Are you getting my point? So yeah, we have discussed this one. Suppose this is P external, this one is your piston, you are doing compression. So your P external is very slightly higher than your P internal. Okay, nearly equal, you can understand. P internal, then what happens is that when you have only a slight change of P external, when you have higher P external is higher, then you are doing compression, but your pressure is not much different. P internal and P external are very much different. You can write it as the P external is equal to P internal plus dP. You can write it as. That means a very small change which can be reversed back. If you change only a small amount of pressure, you can also do the expansion. That means system is under mechanical equilibrium at all the stages. So when you bring that change, this means 5 liter to 1 liter compression, when you are doing with a very infinitesimal change in the pressure, that means that you are maintaining the system at every point in equilibrium, mechanical equilibrium with the surroundings. In that case, you will not experience any change in temperature. Okay, your temperature will be same. It will be maintained. That is how, when we discuss the work done in reversible process, it is always higher because there is a less loss of energy. Here, what is happening? There is a change in energy. Is that okay?
Okay, sir.
Understand? Or you are
Yes,
just
sir.
giving it up? Okay, I will give you a hint. Now it is given to you, right? There is a sudden change in the volume from 5 liter to 1 liter. In one go, you are doing this one. Okay, you are fastly compressing it. Whereas when you are doing it in the reversible process, you will do that same thing in 1,000 steps. Suppose 1,000 small steps you are doing, you are bringing up to that change. Each time you are only going here, you are bringing at 4 liters of uh, change in the volume, whereas each time if you are doing only 4 ml change.
It's a clear, sir.
Clear?
Yes, sir.
So in that case, your mechanical equilibrium is maintained at each time and the temperature does not change. Okay. When you have
Okay, sir.
when you does not have rising temperature, your entropy, the change in entropy, you will not have change in entropy. Here, since the temperature is rising, entropy also decreases. So that part, the contribution of temperature for the entropy is this one. Contribution of volume for the entropy is this one. So overall, the contribution from the volume change, contribution for the temperature change, you will get the answer this way. Is that okay?
Okay, sir.
Suppose if you do not have any change in temperature, what is the total entropy change?
Only due to the volume one.
Only due to the volume. Okay. So these figures are okay. So
Yes, sir.
today I will upload one textbook. Okay. In the
Okay, sir.
Google Classroom, you please follow the textbook. I find it is one of the very interesting textbook because so this kind of figures every time possible that you are giving a very nice pictorial representation for you to understand.
Okay, sir. Thank you, sir.
Whenever you want, I suggest you that first uh, have a read of this book and then go for the any other next higher level books. Means your concept will be very clear. So now take this question. Yesterday also we have discussed, but the question was incomplete. Now I guess you can able to answer this question. This is a
So we
CSI.
have to sum up the entropy change due to the volume change and that of the temperature change.
Yeah, because delta
We have
S.
to use that formula.
Because you are asked B to C, so in the B to C you have a change in temperature as well and change in volume as well.
He said the previous expression.
Hmm.
So
Right,
first
please
we
write
will discuss for
the
temperature, then
value
we'll
for
for
delta. Someone tell the value for delta S. Means the formula that you will use for delta S.
delta S is equals to
Uh,
S is equals to
NCV
NR
N
NR ln
NCV
VS by
learn
VS.
Hmm. NCV ln
uh, uh, T2 by
Two by
T1.
hmm? You are asked for B to C. This is B
T
to C.
T3 by
Sorry, sir. T2 by T3.
T2 by T3 or
T3
T3 by
T3
T3
by
T3
T3
by
by
T2.
Hmm. That's it. That's it.
No, plus
plus n
Plus.
nr ln of
NR
Hmm.
ln of
hello
Hmm.
V1 by no no wait sir. V2 by V1 by V2.
V1 by V2. So this is how you can measure the overall entropy change, right?
Yes, sir.
Okay. So for these options was given wrong yesterday, so we got confused. So now it is clear to you, right?
Yes,
When
sir.
to use which formula, how to measure the change in entropy, under what conditions, means in different conditions, how you can measure the change in entropy. I hope it should be clear to you. Is that okay?
Yes, sir.
Okay, fine. Then we are moving on. So now entropy. So whatever we have discussed so far, entropy change due to temperature change, or entropy change due to due to volume change. All these are when you have a same phase. Okay, when your gas is compressed, but the final stage of the system is again gaseous state only, or liquid to liquid, or solid to solid. There is no phase change. You know the liquefaction of gases, right? When you apply the high pressure, some of the gases they go condense and form liquid. Is that true?
He said that Clausius-Clapeyron equation.
Okay. So there is a change in there is a possibility for change in the phase when you are changing when you are doing volume changes, right? So whatever we have discussed so far, the change, entropy change due to volume or temperature, that is applicable only when you have the same phase. When you have a different phase, when you experience a change in the phase, then you have to consider that delta S is equal to, delta S is equal to, from where we have started, the thermodynamic definition of entropy, Q upon T. Okay, Q reversible, you can consider the change in the Q or dq. So what is the dq upon temperature? Okay, so when you have a boiling temperature, when you take your substance to the boiling temperature, what it happens is that it will evaporate, right? The liquid boils to form vapor. That is the point at which the liquid boils to form the vapor is the boiling point, right? So if this temperature is the boiling point of your liquid, your final state of the liquid is vapor. There is a phase change. Understand? Suppose this figure you can follow. This is liquid form. Okay, when it is melted, when you brought that to the TB value, means temperature, boiling temperature, it will go and form a vapor. In that case, entropy change due to the change in the phase can be calculated, because since it is that is called as delta S of vaporization. Okay, the change in entropy due to vaporization, which will be equal to, from this formula you can write it as, whenever you are doing your reaction or any phase change at constant pressure, the enthalpy definition. If you don't know also, you remember now, the enthalpy definition is energy supplied at constant pressure. Understand? Energy supplied at constant pressure is enthalpy. So here all these things we are doing at constant temperature. So dq reversible, can I write it as delta H vaporization? Is that okay?
Okay, sir.
So when you have if you experience a phase change, this is how you need to calculate the entropy change. Similarly, when you are freezing the liquid, when the liquid reaches its freezing point, it goes and forms a solid phase of it. In that case, the same formula, from dq reversible, since you are supplying energy at constant pressure, you can write it as a delta H fusion. So remember these formulas, these are really very important for you to. So whenever you have a temperature change or volume change, there is a other formula for calculating the entropy. In case if you, in the process, if you experience a change in phase, you have to include the entropy change due to change in phase also. So this figure will explain you in much better way. So when you are increasing the temperature, the entropy will increase, right? Because disorderness of the system will increase. You have a solid, when you are increasing the temperature, so until this point, until you are reaching the melting point, how will you measure the entropy change? You will measure the entropy change by considering the temperature change, NCV T2 by ln T2 by T1, and then by also considering the volume change, if it is at all. Okay, if there is any volume change, or if there is any appreciable volume change, then you will consider. So your delta S will be, you will have two formulas. One is delta S due to temperature change plus delta S due to volume change. And then if you are doing this one at this point, your temperature is this one, slightly above the melting point, then you have to consider also the entropy change due to this phase change, plus the entropy change due to phase change. Is that clear?
So
Suppose
phase change means the previous formula.
phase change means, yes, phase change is this formula. Suppose we
So we
are
have to sum up all the three, sir.
all the three, yes.
Okay, sir.
So yeah, the axis itself is showing, right? Entropy is increasing, and after this there is a again an abrupt change in the entropy. The overall entropy change at the melting point are just above the melting point will be sum of the entropy change due to change in temperature and due to change in volume if it is there, and then due to change in phase. Understand?
Yes, sir.
Suppose this is -4, okay? -4 degrees centigrade, and you are dealing with the ice. So you are increasing the temperature up to this one is, you can consider it as above the freezing point. You can consider it as 1 degree centigrade, okay? At 1 degree centigrade, it is just above the freezing point of water, 0 degree centigrade. So you are, if you are asked that calculate the change in entropy from -4 degree centigrade to 1 degree centigrade, what you will do? -4
We
degree
have
to 1
to sum up
degree.
the entropy change due to the temperature change and the volume change and also the phase change.
Phase change. So three changes, all these three stages you need to consider. Similarly, liquid also. If you are given that your ice is heated to become the vapor, okay. Suppose the temperature range that much is given to you, then you have to change. You have to calculate all these stages. Stage 1 here 2, and then this phase change, and then the temperature, the entropy change due to temperature here, volume here. You cannot directly calculate the temperature change from here to here because the volume change will be different from here to here, right? When your solid is just becoming liquid, your volume change will be only very small. Whereas when liquid is expanding, there is a little change in the volume, but here you will have a very appreciable change in the volume. You can clearly see from the pictorial representation here that this is a test tube, small test tube. This is the volume of it, and this is another small test tube. There is only a small change in the volume, whereas when it went to the liquid to the vapor phase, it occupied a very huge amount of volume. Understand? So your volume contribution for the entropy change is very much appreciable at this stage. Is that clear?
Sir, the volume of the gas, that part only.
The volume of the gas
Will
is
it be
always,
liquefied gas?
no. So no liquefied gas. This is volume of the liquid. Okay. When your liquid is, suppose your water is boiled above 100 degrees centigrade, it will become vapor, right?
Yes, sir, but how do we calculate the volume?
The volume will be given to you. So if
Sir,
there is
suppose
a,
if they are not given me, shall we take the volume of the gas as the volume of the container, like considering the ideal gas?
yeah, okay, yes, you can consider if it is not given to you.
Then okay, sir.
Okay.
Yes, sir.
The thing
So
you need
one
to
question.
remember here is volume of the gas is always very high than volume of the liquid, which is nearly same as volume of the solid. Understand?
Yes, sir.
So remember this point. This is always valid. Understand?
So one
Yes,
question,
sir.
sir.
Clear.
Yeah, if
Uh,
you have anyone, if you have doubt, you can ask me because all the entropy change is included in this figure. This is, I think, one of the best pictorial representation.
excuse me, sir.
Yes, please.
Yes, sir. Today morning I have seen a question from GATE, which is
Okay.
this concept. So what is given there is they have given the change in entropy,
Mm-hmm.
and so the process is melting of ice. The same type
Melting of
question,
ice.
melting
Okay.
of ice at
Okay.
the temperature of 273 Kelvin and 1
Okay.
atmospheric pressure. The
Okay.
change in entropy is 28.80 calories K inverse, and
Okay.
they given, okay, we have to find the number of moles.
Number of moles.
Yeah, they have given the change in entropy, they have given the temperature, and also the um, heat of fusion.
Okay.
So they are asking for moles. Is there any formula for that?
No, no, no. See, the temperature is 273.
Yes, 273 Kelvin.
At 273 Kelvin, you are given delta S.
Yeah, delta S. Delta S is 28.80 calories K
Hmm.
inverse,
Hmm. Okay.
and the heat of fusion is 80 calories G inverse.
Okay. I guess it will be your sum of delta H fusion is given to you.
Yeah, heat of fusion.
No other information.
Molecular weight of water is 18 gram per mole. 1 atmospheric pressure.
Mm-hmm.
So I searched some formulas, but I didn't get relation between the moles and change in entropy in
Okay, I
respect.
guess it must be some of maybe you were given with the CV value of the water.
No, sir, nothing is given. This is from GATE 2019.
Okay, I'll have a look at that question.
Sure, sir.
Hmm?
Akka, can you repeat the question one more time?
The given values.
Yes, Akka.
So atomic pressure is 1, temperature is 273 Kelvin,
Okay, Akka, then.
entropy change equal to 28.80 calories K inverse, capital K inverse. Then
Okay, Akka.
heat of fusion 80 calories G inverse, small g inverse. So an answer was
G
given
inverse.
G inverse, small g inverse, 80 calories G inverse 1. Inverse 1. The answer was given as 5.4 to 5.55.
Yeah, yeah, okay. So, so
I don't know
if
how
I,
method.
no problem, no problem. I can solve that question and explain to you.
Sure,
The
sir. Thank you.
concept is here only, but
Yeah, yes, sir. That only I asked now.
hmm. Okay, well, means probably if I can solve that question, if I can see and solve that question, we can get it. I'll have that look at that question. You can also have maybe you can, if you can able to solve it. Okay.
Sure, sir.
So now, so yesterday,
Sir,
yes,
excuse me,
yes,
sir.
yes,
Sir,
yes.
can you go back 2 slides? The next one more slide, sir. Previous slide. Just a minute, sir. Actually, I got disconnected, so just I can have a look. So, one
You
minute.
want to copy this question?
No, just 1 minute, sir.
Okay, no problem.
From B to C, there is a change in volume and temperature. So that is why we are taking this as the
Yeah.
summation, right?
Yes, yes.
Okay, fine, fine. Okay, sir. We can proceed.
Is that okay up to here?
Yes, sir. Yes.
Okay. So yesterday we have discussed also the entropy of mixing of gases. Okay. So we will have a little bit more details about that one. When you are mixing the gases, when you are measuring the entropy of mixing of gases, remember that so we are considering the ideal mixing. You know, right? The ideal solutions you might have read when you mix the A and B, solution A and solution B, the overall volume should not change. That then you call it as an ideal solution, right? There is no
Yes,
excess
sir.
change. Similarly, here also you are considering that when you are mixing two gases, there is no reaction between two gases. For a reaction between gases, you can consider as nitrogen and hydrogen. If you mix, they will form ammonia at certain conditions. Okay. So like that here, suppose if you mix nitrogen and helium or nitrogen and argon, they will not mix. They will not form any other product. So there, you should always look at the point that there is no chemical reaction and the resultant gas is ideal, then only we can apply this the formula that we have practiced yesterday. So when you have that mixing, your resultant volume is, the change in the resultant volume is 0, and the change in the enthalpy is also 0. Understand, there is no heat exchange because both are ideal gases. Their interactions are very weak.
Sir, but we should take equal volume of gases, correct, sir?
Take any one. Equal volume, why do you consider equal volume? Equal moles we can say, any number of moles you can take, right? Take different
Like
volumes.
considering Avogadro's
Okay.
at last, sir. Equal volume of gases.
1 mole takes 22.4 liters, right?
Yeah, sir.
Yes, sir.
Yeah, if you take one as 1 mole, another one as half mole, I think there should not be any problem.
Sir, no,
Whatever the
sir. Why we have
resultant
to
value
take the
will be
more?
same, sir.
Yesterday we did a problem in that we are mixing 1 mole of CO2, nitrogen, and 2 moles of some other gas. You remember?
Yes, sir.
Volume, see, when you are having ideal gases, if you mix 1 mole of one gas and a half mole of other gas, the overall volume will be sum of those two, not nothing higher. I don't think that you need to take equal volumes.
Okay, sir. Sum of the volumes. Okay, sir.
Yeah, that's what, right? V1 plus V2 should not be uh, greater than that initial volumes. Means suppose you are mixing 5 liter and 3 liter, the final volume should be 8 only, not 8.5 or 8.2 or 7.8 something. That is what the delta Vx mix 0, delta V mixing 0, this one.
Okay, sir. Clear.
Similarly, delta H mixing, because you know that the ideal gases in terms of that they does not interact with each other. There
Yes,
is
sir.
no attractions or there is no repulsions between them, so the energy exchange is 0. So delta H mixing is 0 for the for when you are mixing the two gases in ideal conditions. And another thing is that we are doing that at constant temperature and constant pressure. Okay. So remember this. This is
Okay,
the
sir.
condition where we are doing at constant temperature and constant pressure, and then the entropy of the mixture should be positive. You know why?
Sir, delta S should be positive for a reaction to be spontaneous.
This is the spontaneous condition. Another one, this one is also
Spontaneous.
spontaneous condition, right? Delta G mixing is spontaneous. Delta G mixing negative is a spontaneous condition. So these are the conditions must be satisfied for you want to use this formula when you want to calculate the change in entropy of the mixture. Understand?
Yes, sir. Clear.
Okay. So now you look at the free energy of mixing. You can simply derive it from this equation. You know this equation, right? The relation between entropy, enthalpy, and then free energy. This is very
Yes, sir.
important
Yes.
equation. We have also solved one question, that graphical question based on this. So just now we have seen that under the ideal conditions of mixing, your delta H mixing is 0. So this will turn up into this equation, and from this expression for this is known to us minus T. Delta S mixing is minus NR
Minus n a summation of chi
X.
xi
Xi
lakh
ln
xi.
xi.
You just substitute that one here. So this is what you will get for the delta G mixing. Okay, is that okay?
Yes, sir.
So whenever if you are asked for the free energy of mixing, you can take this one. Xi mole fraction of these mole fraction values are always less than 1, right?
Yes, sir. Yes.
When you are having always less than 1, your ln Xi is negative. because logarithm 1 is 0. Okay, if you go anything below that 1, you will get a negative value for logarithmic value. So this will end up you giving the negative value for xi. So since it gives the negative value, overall you will get is negative. Understand? That's how it works.
Fine, sir.
Sir, can you please go back to that phase change entropy expression? Okay, sir.
What are you doing? You are copying or what I don't
No, sir,
understand.
just no, sir. I want to have a recap.
Okay. Then what about this Clausius-Clapeyron equation? Shall we go for it or
So
Next
next
class,
class.
We'll do it in next class.
because yeah, we have some really important points here. Okay, fine. If you as you wish. Okay. So there is
okay,
also
sir.
one thing I would like to ask from you guys that should we completely thermodynamics we should do, or you want me to go to the molecular spectroscopy?
So first thermodynamics, then we can go, sir, because it would get mixed up if you combine both.
Yeah, means we have only 3 classes left as per schedule. If you want, I can do is that what I can do is I can complete the thermodynamics. I can give you a complete practice of the questions. That is option number one. Option number two will be I will finish the thermodynamics in next one class and go for a quick uh, uh, some quick coverage of molecular spectroscopy, some rotational or vibrational spectroscopy. The choice is yours. If you want me to complete this thermodynamics chapter also, that is fine. I feel in at least one chapter you can have a clear idea.
Okay, sir, you can then complete thermodynamics.
Thermodynamics you
We
can
have
complete.
3 classes left, right?
3 classes left, yes.
So then in one we can complete it, and then we can start that molecular spectroscopy.
That one, no?
Yes, sir.
Then you will have you need to practice the questions by yourself.
Okay, sir. Fine. If you have doubt,
Okay,
we'll ask
sir.
you.
Hmm?
If we have any doubt, we'll contact you, sir.
That is also fine. If you have any doubt, you can contact me. You can put that question in the GCR, or you can send email to me. I will respond to you. If you anytime if you come to the campus, you can meet me. That's not a problem at all. Because how many of you have already read the molecular spectroscopy? The
We had it in UG, sir, like the basics one.
the rotational spectroscopy and
Yes,
vibrational.
IR, yes, sir, vibrational and UV, also the NMR and mass spectrometry.
Now, this is different from organic spectroscopy, okay?
No, sir, we had the basic principles and we solved just a few questions.
Okay. So the numericals.
Yes, sir.
Not exactly numericals and all, sir. We just know the very basic levels, so not so deep.
Yes, sir, yes.
So what is what I had done and
We
what
just learned the theory part of somewhat very basic, sir.
Uh, okay.
Sir, if you will start with the first term only, and it will be good.
Okay, fine. I will try to do one thing. Only one or two this Clausius-Clapeyron equation, and then that partial molar properties. These two are only left. I can finish it in. If you want to have a clear idea about it, I will take 1 hour. If you want to complete it in fast way, I can finish it both in 1 hour.
So no, sir, clear, sir, because in competitive exam and all, thermodynamics is the most like the
So
complicated
thermodynamics,
part.
yeah, and it can be scoring for you. That's what I'm telling. It's
Yes,
easy.
sir, but it's kind of confusing, sir, at the time of examination and all.
Okay, okay. So I will post a textbook today. Okay. What I
Yeah, okay,
suggest
sir.
you all is, since you guys are really interested, uh, uh, I suggest you to solve the problems given in that, not only the problems in the end of the textbook. Those are only questions given. Also, the examples that are given. Understand? Because
Yes, sir.
I have seen in net the questions based on the examples in the textbook also.
Okay, sir.
Sir,
Hmm.
excuse me, sir. For jam and all, we had like 15 years previous year solved question papers.
Okay.
Arihant book and all was there. Sir, is there any book you can suggest for net, sir, like which will be containing the previous year solved question papers and all?
Yeah, there are books. I think I
Anyone
don't
you can
remember the
suggest?
publication company. If you want, I also have some. I collected from some web. I'll suggest you one thing. One website is there, and also if you want, I will upload one PDF. It has around 5 6 years of solved questions. Not
Yes, sir, that would be good.
not but it is not based on chapter. It is like based on the paper 2015 paper. It has a complete solution. Then what the problem for you is that if you are practicing thermodynamics, each time you have to, for each paper you have to find initially the question of thermodynamics, then go for the solution.
There actually no book is having this categorized section wise and all. Sir, every book it is like they give every all the questions are being shuffled only. No book is like
I
thermodynamics.
remember. I remember one of the guys I met. They were using some this textbook, not the textbook. The one book in which selected topics are given. In that topic-wise answers are there.
Which one, sir? Can you please tell it in next
Uh,
class?
I don't remember it. You just you try to find it in Amazon itself. If I will also try to find it and let you know. But you will get it in Amazon itself. You look for chapter-wise answers, chapter-wise solved examples. It will be like that. Okay. But in
So,
that book, there are only selected chapters given. I don't know whether they have given thermodynamics or not.
so can you suggest some authors who have read like books?
I don't know. I could not get you. Could you please repeat?
So can you suggest some authors of those books which you
Okay,
told now?
usually I can suggest you today the one book I post you. Okay, you go through the examples of that one. That will clear you up to the bachelor's. For JAM exam you can clear from that book. I am sure in that. Okay, that book also clarify you basics because the pictorial representation is excellent in that. And always you have the Peter Atkins physical chemistry. That is the most standard one. And we have for Indian version, the physical principles of physical chemistry, something by
Puri
Puri
Sharma.
Sharma.
Purian Sharma? Is it Purian
Yeah, it
Sharma?
is very good book. Especially the examples discussed in that book are really nice. Okay, now we have some discussion, right? What you can do is that you open of these textbooks and do the examples only. Don't read the theory. Do the examples or try to understand the graphs. Then it will be clear. I think if you, based on the content that I am giving to you, if you have a practice of some questions, you will have a clear idea about it. Only one or two revisions you need to make after 2 3 months if you forget something.
Okay, sir.
I
Okay,
also
sir. Sure.
have some
Thank you.
downloaded question paper, downloaded notes. Okay, I can give you that one also. I don't know whether I can put it in this platform or not. Wait a minute, I will tell you. Okay, write chemistryabc.com.
What light chemistry here?
Chemistryabc.com.
Chemistry ABC? Chemistryabc.com.
You know this already?
No, sir, no.
This is
Chemistryabc.com.
this is a
Please
website, sir.
I don't know whether you can find textbooks or not in this, but this is like the coaching centers are there now. There are so many coaching centers that are famous for CSR net. All the coaching center notes are available in that website for free. Understand?
Yes,
Then
sir.
all
It
the
will make sense.
coaching and then I don't understand.
Chemistryabc.com. There are several coaching centers, right? You know that
Yeah, yes, sir, yes.
each coaching center they give a notes
Yes,
that
sir,
means
yes. They
the
give that
note,
notes,
yeah, yeah, that,
compilations.
it will not contain lot of description. Directly the formulas, what are the important content only will be there. That will be useful for you for the revision. Once you understand the topic,
Okay, sir.
some if there is some tricks or something you can get from there also. So this one for the content you can go for this. Okay.
Okay, sir.
Okay, sir, okay.
Okay, sir. Thank you, sir.
For quick
Thank you.
understanding
Thank you, sir.
of the subject, this is useful. And I will also upload this Peter Atkins and the book that I am referring you. All these I will upload today itself. I have uploaded all the first three classes slides. Got it?
Yeah, sir. Yeah, sir.
Hmm. Today's one also I will upload. If you need any other things, you can let me know.
Okay, sir. Thank you, sir.
Only I can suggest you is that practice more questions. If you are feeling it difficult, start from IIT JAM questions, then come to this ESR net questions.
Okay, sir.
Thank you.
Okay, sir. Thank you, sir.
Thank you.
Thank you so much, sir.
Thank you, sir. Can we leave, sir?
Yeah, yeah. Thank you for
Thank
joining.
you.
Yeah, sir.
Thank you, sir.
Thank you, sir.
Hello, Akka. Hello.
Hello. Hello.
Akka, can I have your contact number?
அம்மா ரெக்கார்டிங்ல இருக்குடா.
Akka, what?
I'll mail you. I'll mail you, okay?
Yeah, yeah, okay, okay, Akka.